And let's start by recalling that logarithms and exponential functions are inversely related. So if I have something like 2 to the power of x equals y, then the inverse of that is log base 2 of y equals x. So just to recall what a logarithm is basically the power to which you would have to raise the base in order to get that other result. So for instance, if we had 2 to the third power equals 8, that would be in logarithmic form log base 2 of 8 equals 3. So you can see the answer is the exponent, right? Like the base of 2, if you want to get a result of 8, you've got to raise it to the power of 3. Okay, so that's just a little recall on what a logarithm is. It's not some kind of, foreign entity. It's just an exponent. And because they're inversely related, if you graph them both on the same xy coordinate plane, you will see that they're symmetric across the identity function y equals x. So we might need to recall a little bit about inverse functions. Inverse functions have the effect is that the x's and y's swap places. So if you have a function x and then you have the domain of f and the range of f, and then you have an inverse function, f inverse of x, then the domain of f inverse is actually the range of f, and the range of f inverse is the domain of f. In other words, x's and y's switch places. So if I have an exponential, remember exponentials are J-curves like this, and the logarithm then would be a reflection across the y equals x identity line, and so it would look something like this. And when you're graphing functions, you can start off with the basic function and move them around with transformations. We learned about transformations before with things like linear equations and parabolas and cubic functions and square roots and cubic roots. So we're going to be applying the same principles when we graph our logarithmic functions. So let's recall how to do transformations. There are different types. We have shifting, and you can go up and down, you can go left and right, or right and left, and you can reflect. You can take something that is like this and reflect it across the y-axis upside down. You can take something like that same thing, like a J-curve, and reflect it across the x-axis, or I meant to say the y-axis. And what else can we do? We can stretch things and compress things or shrink them. And so I guess the easier one to use as an illustration would be a parabola. So if we had a parabola like this that's like y equals x squared, then if you put something like 2 in front of the x squared, then it's going to stretch vertically. I'm doing really, really rough sketches just as a quick review. Being a little sloppy here. So we have a skinnier version of that parabola when you put 2 in front of it, or if you have something like 1/2 in front of it, it will actually cause a widening or a compressing or shrinking vertically effect. And then you could have things like, say this is y equals x squared again, as like, say this, then it can cause this to happen, which is a vertical stretch. But we call that a when the 2 is on the inside, or the stretching factor is on the inside with x, we call that a horizontal shrinking, because you could squish it in horizontally. But it also can be viewed as a vertical stretch once you simplify it. So things like that. We also had the opposite effect, 1/2 x quantity squared would give you 1/4 x squared if you simplified it. So what would happen is, if this was your original parent function, then you would have something getting squattier, shrinking. You could either call that a vertical compression, or you can view it, when it's in this form, you would view that as a horizontal stretching effect. So all of these things still apply. I guess I should talk about shifting again real quick. So if you had something like y equals x squared, and then you did a +2 on the outside of it, that would move it up. Or if you did a -2 on the outside of it, that would move it down. Or if you had something like x minus 2 squared, it would actually move it the opposite of what you would think. It would move it horizontally to the right. If you had a positive in there, you would actually be moving to the left. So all these things, reflections, let's see, y equals x squared. If you put a negative in front of it, it's going to flip across the y-axis. I meant to say the x-axis. It's going to flip vertically across the x-axis. And if you were to put the negative on the inside before you take the exponent, then it would reflect it across the y-axis, or in other words, a horizontal flip. So all these things, they apply still with logarithms. So we're going to put all that together. And so let's review the parent function. F of x equals the log, say, I don't know, base 10 of x. Log, or we'll do the one that's in the book just to start with. So if you have log base 2 of x, then you've got something that looks like this. And there are certain key points that are always on these graphs, depending on your base. Here our base is 2, and so we would have the point, there's one point that you have no matter what the base is, it never changes, it's 1, 0. Then you have the point 2, 1, so the base and 1, and then you have also a point down here, which would be the reciprocal of the base, and -1. So if we plug these, if we try to do an XY table, we could do, let's plug in 1 for x. So what's going to happen? Then you're going to have f of 1, which would be the log base 2 of 1 as an input, right? And so if you think about it in exponential form, because remember, a logarithm is the power to which you have to raise the base in order to get the input. We also call that an argument sometimes. So if I convert that expression to an exponential, and this is my y value, right? So 2 to the power of y is equal to 1, right? So what would you have to raise y to, or excuse me, what would you have to raise the base 2 to? What power would you need here to get 1? You would need 0, right? So that means y equals 0 when you plug in 1, right? So f of 1 is 0, and that's why you always have that point, that coordinate, like this right here, because whenever you raise any base to the power of 0, you're going to get 1. So no matter what the base is of your logarithm, you're always going to have that point, 1, 0. That's a given. All right, then you have, let's plug in 2. So plugging in 2, That's log base 2 of 2. So 2 is the input and it's the base. So if we rewrote this in exponential form, this is your input, right? So you would have, or rather I meant to say this is your y value. So it's a way of saying y equals the log base 2 of 2. So if you rewrote that in exponential form, you would write it as 2 to the power of y equals 2. So what do you have to raise any base to in order to get itself as a result? That means y equals 1, right? So you're always going to have that point where you have the base and then the output value 1. Then we have 1/2. So let's plug in 1/2 and see what happens. So if I plug in 1/2 right here, and then this is 1/2, what do I have to raise to, or what power do I need to raise to and get its reciprocal? Well, remember, whenever you want to flip a base, so if we rewrite this base as 2 over 1 to the power of y, and you want to flip that base, you can, and then you just make your exponent the opposite sign of what it originally was. So, bringing this down, you have the base 1/2 to the power of 1, and negative y then would be negative, or negative y would be positive 1 then. And then you could divide both sides by negative 1 and get y equals negative 1. Or you could have seen it a different way. Let me back up and try it another way. So let's say from 2 to the power of y equals 1, or what did I have? 2 to the power of y equals 1/2. Maybe I want to flip this base, right? So how about if I do, instead of 1/2 to the power of 1, maybe I'll do 2 over 1 to the power of negative 1, or just 2 to the power of negative 1, which you don't actually need parentheses then. And bringing this down, 2 to the power of y, well, the bases are the same. I'll write it a little neater. The bases are the same, which means their exponents must be the same. So then you always get, with an input of 1/2, you always get a result of negative 1. Right, so you can change the base, and let's say I make this a base 3, then we will have this change to a 3, and this change to a 3. This point always stays the same regardless of the base, because again, 3 to the power of 0 is going to be 1. Right, so that's why you see on the general graph in the image on the page 416 in the textbook, you see if this is your base, I think they used A here to represent the base, which I think they should have used B, just saying, but they used A, so then they said, well, then you're always going to have A comma 1 and 1 over A comma negative 1, and of course the given token point, I guess you could say, 1 comma 0. Alright, so now that we know about the parent function, let's start working on some problems. So that, remember, when you have something being added or subtracted on the input, it moves it left or right, and it moves the opposite of the direction you might think for the horizontal, so it's going to go to the right 1 unit. So this original that had the points, what was it, 2 comma 1, 1/2 comma negative 1, and of course 1 comma 0, that's all going to just shift over 1 unit. So if you just add 1 to all the x values and keep the y values the same, because you're not moving it up or down, you're just moving it to the right. So that would end up looking like, here's my asymptote, my original vertical asymptote that the graph never touches, right? Now that asymptote is going to be moved over 1 unit. So now my asymptote's going to go through x equals 1. and then I'm going to have this happening, and I'm going to have the point 3, 1, and now I'm going to have 2, 0, and what happens if you add 1 to 1/2? Then it becomes 3/2, right? -1. And so let's test this out. Okay, so I'm going to take this and I'm going to do my XY coordinates. So if I have the input of 3, what happens? I have log base 2 of 3 minus 1. So that would be log base 2 of 2. So what power would I have to raise this? What power would I need to raise this base in order to get that result? Yep, you're right. 2 to the power of 1 equals 2. So that is why 3, 1 is actually correct. Ding. Now how about if we plug in 2, right? So we'll check this point out. 2, what happens? You'll have log base 2 of 2 minus 1, which simplifies to log base 2 of 1. So what do I have to do? I have to do 2 to the power of 0 to get 1, right? So that means that my y value is 0. Ding! Let's do the last one, 3/2, or 1.5. 3/2. Plug that in, log base 2 of 3 over 2 minus 2 over 2, okay, because 1 is, you can always rewrite 1 as something over itself. So to get that common denominator, I have 2 over 2, and when I subtract the numerators, I get a sum of -1, or not negative, I don't know why I said negative, I didn't mean that. You get 1/2. Okay, so what do I have to raise 2 in order to get 1/2? Yep, that's the reciprocal. So reciprocals are easy to get if you just change the sign of the, so instead of 2 to the 1, you would want 2 to the -1, right? So that would give you, if you had 2 to the -1, that would flip your reciprocal, okay? So that is -1. Ding! Awesome. See, transformations, they're easy. So let's do another one. Let's say number 50 says f of x equals the log base 2 of -x. All right, so we're putting a negative on the parent function inside the input. We're doing a negative multiplier, which is going to cause a reflection, and it'll be a horizontal reflection since it's happening to the x values. And so instead of having this, we're going to have this, something like that at least. And so all the points here, all the points over here are going to just flop across that y-axis. So we had the points 2, 1, 1, 0, and 1/2, -1. They're going to flip across the y-axis. So what happens over here, we just have negative. On this side, we have negative x values, right? The y values are not going to change, just the x values. So I'm going to have the point -1/2, -1, and -1, 0, and 2, or -2, 1. And really, this point should be a little higher, just saying, should be a little higher. And